Good day, class. In the previous video, we learned one of the most important results in derivatives, and that is the mean value theorem. Now in this video, we will be dealing with consequences of the mean value theorem. We will be using these results in finding what we will call the relative extrema of a function. Now without further ado, let's begin. So what is a relative extrema? Now if I have a function f and a real number c, we say that a function will have a relative maximum at c if there exists an open interval I containing c such that f is defined for all x in I, and for all x in my interval, the evaluation of f at x will always be smaller than f of c, or the evaluation of f at c is the biggest among all evaluations inside the interval. Do note that c is in the open interval I, so it truly is the biggest in the whole interval. So the biggest part comes from the idea of a maxima. The relative comes from the existence of the open interval. It basically means that you are the biggest on some neighborhood, not necessarily the biggest in the whole domain of your function f, but at least relatively you are the greatest. Of course, you can also talk about the relative minimum, which is relatively the smallest, and that is f of c will be smaller than any evaluation of f at the interval I. Collectively, we call this the relative extrema of your function. Extremum if you have either a relative maximum or a relative minimum. Now this is best described through a graph, so let's have the following demonstration. I have the following function f, which is defined only from c1 to c6. You're not defined at c2, but you're defined on every single point from c1 to c6. So what is a relative maximum? You are a relative maximum if you can find some ball where it is a peak. In this case, if I make a ball small enough, notice that it will be the biggest in that ball. This one is also the biggest in this ball. However, notice this will be bigger than this, but it doesn't matter. As long as on some neighborhood it is the locally maximal, then you are a relative max. A relative min is the same. A relative min will be a point in such that if you make a ball, it will be the smallest in that neighborhood. Notice this value is smaller than the value at this point, but it doesn't matter because the word relative means the existence of some neighborhood where it is the biggest or the smallest. Now based on our definition, the left point, which is c1, and the right point c6 are not relative extremas, even though it's kind of big and this is the smallest if you make a ball. However, we are looking for interior points for our relative extrema. It means we will not be considering boundary points in our study. Also, we are not going to be studying things not in the domain, as was indicated in our definition. So we need our point or a relative extrema to be attained. It should be an interior point. It is the biggest on some neighborhood. So again, it is an attained point. It should be defined there. It's an interior point. We don't consider boundaries. And it is the biggest and smallest in some neighborhood. And thus, in this graph, we only have C3, C4, and C5 as our relative extrema. Now let's have a few terminologies. So, in this case, we say that f has a relative extremum at c. The point c f of c is called the relative extremum point. while the y value f of c is the relative extremum value. So you have a relative extremum at a point x. The relative extremum value of f is the y value, and the point will be cf of c. This is more for clarity, and so that you'll be able to read the module and the literature easily. Now, what is the goal? Now, we notice that relative extrema, especially in the graphical sense, is very easy to see as long as you can make a ball where it's the biggest or the smallest, attain an interior point, you will have a relative extrema. However, to be honest, it's not really easy to graph. So how do we find the relative extrema of a function without graphing? The answer lies in the following important theorem. If a function f has a relative extremum point at c, then either the derivative is 0 or it does not exist. This is an important observation when you look at relative extremum points. For example, this is the graph of y equal to negative x squared. You will notice easily at the graph that it has a relative maximum at the origin, and the theorem states that the x value where it happened at 0, if you evaluate the derivative at that point, it will be 0 or non-existent. And that's true. The derivative of my function is negative 2x, and if you evaluate it at the relative extremum point, that will be 0. Also, if I have the absolute value of x minus 3, clearly you will have a relative minimum at this point, which is just a 3, the one that gave you a 0. If you try to get the derivative of your function, you will see that it will not be differentiable at 3, and true enough, relative extrema will imply that the derivative will be 0 or non-existent at the x value. Now, this is a very powerful theorem because this is a sifting theorem. Essentially, it tells us that when you have a relative extremum point, a necessary condition is that the derivative is either 0 or non-existent. However, a lot of people will have problem dealing with the implication here. So let me demonstrate that to the following definition. Instead of calling those things that have 0 as their derivative or undefined as relative extrema, let us call them a critical number. Critical numbers are numbers in the domain. Of course, it should be in the domain because relative extremas are attained points, and that it satisfies the property that we have before, that the derivative is 0 or undefined. The theorem states that if you have the set of x's in the domain, the critical numbers is actually a smaller set, and the set of all x coordinates of the relative extrema is even smaller than the set of critical numbers. If you notice, going back to our previous slide, if you are a relative extrema, or if you are in this set here, then you are in the set of critical numbers. That's what it means. Being an x coordinate of a relative extrema will imply that you are a critical number. Now be careful that the converse is not true, and it means that there are points in the critical numbers that are not x coordinates of relative extrema. For example, the function x cubed, if you get the derivative, that will be 3x squared, and at the origin it will be 0. However, the graph of this function will be the following, and the following will not have a relative maximum or minimum at the origin, clearly, because if you make any size of a ball, there will always be bigger than the origin, and there will always be something smaller than it. Similarly, for the function f of x is equal to cube root of x, the derivative will be 1 over 3 cube root of x squared, with a non-existence at the origin. And again, even though you are a critical number, you do not have a relative extrema at that point. So So what's the point in getting the relative or the critical number? The point is the following. Going back to the previous slide, the domain of f is a very large set. It has infinitely many numbers. And since you want to go from the domain of f to the x-coordinate of the relative extrema, instead of analyzing every single point in the domain, I will first obtain the critical numbers, thus giving you the first gate. In a sense, I will first find critical numbers and thus will sift out the so many points in the domain of my function f. And afterwards, I'll just need to ask which of these critical numbers are truly the x-coordinates of my relative extrema. So that's how we are going to do it. But how? So from real numbers, I can easily obtain critical numbers by solving when is my derivative 0 or when it is a non-existent. But how do I go from the the critical number to a relative extrema? The answer lies under the result given by mean value theorem, which is given by this next section. Let us define what does it mean for you to have an increasing or decreasing function. F is said to be increasing on I or strictly increasing on I if any a, b that satisfy this one, so a smaller a will imply that the evaluation will also be smaller. Increasing essentially means that these inequalities have a direct proportion. A smaller argument will mean a smaller evaluation. A bigger argument means a bigger or equal to evaluation. For strictly increasing, we remove the equal sign here and we'll have strict inequality. For strictly decreasing and decreasing functions, we have the same, and the opposite is what will happen, and that is we have an inverse relationship. A bigger argument will mean a smaller evaluation. This is easily seen as in graphs. When you are decreasing implies that you are somewhat sloping downwards towards the right, and if you're increasing, you're sloping upwards towards the right. For example, this function here is decreasing on the following intervals. It's decreasing from C1 to C2, not including C2, but including C1, because C2 is not defined. It is also decreasing from C3 to C4 and decreasing on C5 to C6. So you will see here that as long as you can see that it is sloping downward, then that part will be decreasing, or f is decreasing on that interval. Be clear, it is incorrect to say that f is decreasing on the union. It's decreasing on this one, which is you have a comma and n, but it is not decreasing here. Primarily because to say that f is decreasing on this set means that if I get a point here and I get another point there, then a smaller argument, it should be bigger, but that is of course wrong in this case. So it's only decreasing on the individual intervals, but not on the union of the sets. Increasing if you are slanting towards the right, upward towards the right. So that's from C2 to C3. Again, we did not include C2, and C4 to C5. So graphically, it's very easy to see whether your function is increasing or decreasing on an interval. You just look at the interval and see whether it is sloping downwards or sloping upwards. But just like critical numbers, we don't want to always graph for us to get increasing or decreasing. Good thing we have mean value theorem. By mean value theorem, we have the following results. If my function f is continuous on the closed and bounded interval ab and differentiable on the open and bounded interval ab, then if the derivative is positive, then you are increasing. Derivative to be negative, it means that you are decreasing, and derivative to be 0 means that you are constant. You will see here that by obtaining the sign of your derivative, you will be able to get whether your function is increasing, decreasing, or constant. Things to remember here are as follows. Number 1, you only need that the derivative is positive on the open interval, and the conclusion will already be increasing on the closed and bounded interval. So positivity for your derivative is only required for the open interval, but increasing will have a conclusion on the closed. This is because of the assumption of continuity. It's the same for the negativity of your derivative to decreasing. It's not that hard to memorize. Just remember, positive means increasing, negative derivative means decreasing. When you are 0, then you are constant. Remember, when you are 0 at a point, we call that a critical number. But this is a strong result because it says that the derivative should be 0 not at a single point, but for every point in an interval. So what it means is that when the derivative is 0, the graph will somewhat flatten out, and that will become a constant function on your interval AB. So remember, having a 0 derivative does not mean you're constant. But if you're 0 for an interval, automatically you are constant on that interval. Unfortunately, we are not going to prove this by mean value theorem, and it will be left as a reading exercise for you to know how this theorem was proved. For example, I have the function x squared. Remember, when you get the derivative, you can obtain 3 conclusions. Number 1, a conclusion on the critical number, a conclusion on when it is increasing, and a conclusion on when it is decreasing. At first glance, those 3 conclusions are somewhat disjoint, but you can actually connect them into one solution. For example, if you remember, since the derivative of f is 2x, when you get its 0, and since 2x is a continuous function, by intermediate value theorem, the 0 will be cutting the interval into the times when it can be positive and when it can be negative. Because by IVT, it says that it cannot cross from positive to negative or from negative to positive without going to 0. That means solving for the critical number or the 0 of your derivative, or that does not exist, actually tells you when to cut your interval. For example, when 2x will be 0 at 0, and you will notice at 0 to infinity, it will always be positive. And when it is at negative infinity to 0, it will always be negative, thus giving us the conclusions that you are increasing not only on the open interval 0 to infinity, but on the closed interval. As I've said before, positivity on the open will imply that you are increasing on the closed, and decreasing on the open will imply negativity on the open interval implies decreasing on the closed interval. Of course, for example, in f of x equal to x cubed, when you try to get the derivative, which is 3x squared, this will have a 0 at the origin. However, since this will always be positive whether you are on the left of 0 or on the right of 0, because you have an x squared here, then that will mean that you are increasing everywhere on R. Just implies that when you have a critical number, you're not always so sure that you will have a change of sign. So we are lucky enough in the previous example that we change from negative to positive. But in this case, if you make the table of signs here, you will notice that for numbers less than 0, it will be positive. For numbers right of 0, it will be positive. Ergo, the zeros in undefineds can be a moment of change, but you are not assured. Sometimes there will be a change in sign, sometimes there will be none. And that is for the increasing and decreasing function. In the next video, we are going to be talking about how we are going to collate what we have learned for relative extrema and critical numbers and increasing and decreasing functions. This is the topic first derivative test for relative extrema, and this is how we are going to cross the chasm between critical numbers and relative extrema. Now I hope you learned well in this video. Stay safe and thank you for watching.